Okay.
The center to center distance between the two gears is 3.62. What is the pitch of the 3 inch?
So outside diameters we're going to work with. Let's say I give you an outside diameter of 4 inches and 5.5 inches, respectively. And I tell you that the distance from center to center is 4.62 inches. It does look kind of like a face, doesn't it? Looks like one of the Minions. So anyway, this is 4 inches. This is 5.5 inches. Remember, the outside diameter goes to the outside edge of the tooth, but the gears overlap. So the amount that they overlap is what's called the working depth. How do I figure that out? Now, what is the radius of this gear? 2 inches, half of my 4. What's the radius of this gear? 2.75. If I add those up, that would be 4.75. Subtracting 4.62 gives me 0.13 inches working depth. Right? So now in our packet, we've got a formula for working depth to pitch. You should. If you don't, then I really screwed up somewhere. Should be on like the second page of the Sprague formulas. Find it? Any other questions off the test? No? Okay, so new stuff. We're going to talk about a little bit of geometry today, starting with our most basic geometric concepts that we talked about a little bit last semester. A point is the most basic, just a location. Now, the next most basic geometric concept comes from taking that point and pulling it through space in a single direction, which creates a line segment. Most people call that a line, but it's really just a segment of a line. It's a piece of a line. Technically, to be a line, it has to go on forever in both directions. Now, in real life, that's not very practical. I mean, nothing can go on forever in both directions. It has to start somewhere, right? So a little more practical than, what's that? A little more practical than just a line or a line segment is a ray. An array is where you take just that point and you pull it in a single direction and just keep going forever and ever. Like, that's why they call sunlight rays, because it starts in the sun, and if it doesn't hit anything, it'll keep going on forever in a straight line. So, we need to talk about these rays, and we need to talk about direction. There are a lot of applications for directions and directional calculations, many of which we don't use and aren't very applicable anymore. One of them was for navigation. If you're navigating north, west, south, east, In navigational terms, 0 degrees is due east, 90 degrees is due north, 180 degrees is due west, and 270 degrees is due south. 360, of course, is back at 0. And that's your directions. Yes. Yeah. Because the 0 is north, isn't it there? Yeah. But anyway, this also applies for like vector analysis. If you're doing any strict vector analysis, you've got a 0 point and so on. It's a little outdated because we don't do a lot of navigational stuff anymore, but it still applies for directions of a ray. To name the direction of the ray, we put that starting point at the center of our little grid here, and then wherever it goes off to, that is its direction. So this ray might have a direction of, well, 28 degrees. If we go from that starting point, that common starting point, create a ray. If we go back to that same starting point and create another ray going in a slightly different direction, or maybe even a radically different direction, what we have created there is an angle. Now the size of that angle can be found in a couple of ways. The original way of finding the size of that angle goes back to these directions again. Let's say this first angle here is at 18 degrees. And the second angle, let's say, is at 46 degrees. So the angle, or the direction, I should say, of the first ray is 18, and the direction of the second ray is 46. The actual angle is the difference in their directions. 46 minus 18 is 28 degrees would be the angle between those rays. So that was the original definition of an angle, is just difference in direction. Now, since navigation and directional stuff like that is not common anymore, this is also for surveying and stuff like that as well. Since it isn't that common anymore, what they've done is they've defined it a little bit differently. Of course, we know if you make a full rotation, that is how many degrees? 360 degrees. And we've started to define angles. Instead of defining this common starting point as a center of a navigational grid or directional grid, they've started defining that as a center of rotation. And started defining the angle as a fraction of a full rotation, or a fraction of 360 degrees. So we know that if it, pretend that's a straight line, that's how many degrees? 180. And we know that if it makes a square corner, that's 90 degrees, and so on, and any fraction thereof. So what you can look at angles in a couple of different ways, as being that difference in direction, or as just a fraction of a full turn or portion of 360 degrees. Both of them are technically accurate, so it's not a huge deal which method you decide to use. So let's look at these angle relationships here. Let's say I have an angle here that is 31 degrees. And I'm going to go back to that common starting point a third time. Construct another angle here that's 62 degrees. So a third ray. What we have created here is something called adjacent angles. Adjacent means next to, or sharing a side. These two angles share, there's two things that must happen to be called adjacent angles. One, they must share a side, which these do. But here, these two angles share a side right here. Are they adjacent angles? No. They must share a side, but they also must share a vertex, which is that common starting point. When we have adjacent angles, we can now start to apply algebra to them. These two angles, I wanted to find this bigger angle Well, 31 and 62 can be added together to get 93 degrees. Which makes sense. If the difference in their direction here was 31 degrees and the difference in direction here is 62 degrees, the total difference in direction would be 93. Or the rotation, if you're thinking of it as rotation, you rotate 62 degrees and rotate another 31, you've rotated 93. So it makes sense for it to add up. Likewise, if I had an angle here that was 79 degrees, and an angle here that was 24 degrees, what's this angle have to be? How'd you find the 55? Yeah, 79 is the whole angle, subtract 24, gives me 55 degrees. So that has to be 55 degrees. Those angles have to add up. So now when we're dealing with these pairs of adjacent angles, we can have some special cases. We have two angles like this that are adjacent and they add up to a straight line. Fancy name for them is called a linear pair. There's a more functional name for them that we use. First of all, let's say this angle here has to be 73 degrees. What's this angle have to be? Yeah, 180 minus 73 or 107. Because we know a straight line is 180 degrees, those two angles must add up. Because adjacent angles add up to the total, they must add up to 180. Even if they're not adjacent, two angles that add up to 180 degrees are what we call supplementary. So if I have this, and this is 111 degrees, what's this have to be? 180 minus 111, which is 69 degrees. Another special case might look like this. Where let's say this is 68 degrees and this is 22 degrees. What do they add up to? 90. They add up to a right angle or a square corner. Those are called complementary. Pretend I didn't butcher my handwriting on that. Complementary. Now, if you're anything like me, you can remember the words supplementary and complementary, but remembering which one's which is kind of tricky. So the way I always remember it is you get complements when you are right. So complements are add up to a right angle. So find complement of 42 degrees. How'd you get that? 90 minus 42, because complements add up to 90, 48 degrees. Not so bad? Okay, well, the geometric concept that we discussed when we did areas and volumes involves things like this. If we're dealing with just two lines, of course, they intersect at a right angle. Well, first of all, if they intersect at one right angle, they form how many? 4. Because if this is 90 degrees here, because this is a straight line, this has to be 90 degrees as well, because they have to add up to 180, don't they? And by the same logic, all of those have to be 90 degrees. This is what we call perpendicular. Adds up to 90 degrees in every direction. Yeah, we'll get to that. That one's coming up. Now, what if we have lines that don't intersect? They're called parallel. Very good. And I should be careful. I said they don't intersect. On a flat plane like this, like the surface of the board or the screen, saying that they don't intersect is adequate because it's two-dimensional. But if it's three-dimensional, that's not adequate. For example, let's say I have a line here and a line here. Do they intersect? Will they intersect? No, they won't. They'll never intersect. Are they parallel? No. But because they're in three dimensions, they won't intersect. They just go in weird directions. But they're not parallel. So saying that two lines don't intersect is not adequate. Technical definition of parallel is everywhere equidistant. That's just a fancy word for always the same distance apart. If they are on a plane or on a graph, yes, they have to have the same slope. In three-dimensional, it's really tough to define slope. In order to define slope, you've got to define a vertical, first of all. And once you define vertical, you've got to define a direction, because you can't just do a rise over run, because you must also form a direction as well. So slope becomes more complex in three dimensions. If I have parallel lines, though, and I cut it with a third line like this, now any line that crosses two or more other lines is called a transversal. There are some angles formed. First of all, let's say I tell you that this is 64 degrees. Well, hang in there. How do I find this one? 180 minus 64, or 116. Now from that same logic, I can find this one here. 180 minus 116 would be 64. And with that same logic, these two angles will always have to be equal. Whenever I have two intersecting lines, the two angles on opposite sides of that intersection must be equal. Those are what we call vertical angles. Don't know why they're called vertical, but they are. Well, vertical, I suppose if they're here, they're up and down. Like this one here, of course, has to be 116 because it's vertical with that one. Opposite side. Also because these two have to add up to 180 and these two have to add up to 180, so it has to be 116. Any guesses what this angle has to be? Yeah, 64. Because if I took this line here and I moved it, it's going to fall right on top of that line. So this angle is going to fall right on top of that angle, so it has to be the same. So that, of course, means this is 116 and 64 and 116. Good stuff, right? There are all sorts of rules for parallel lines cut by a transversal. They go into, they define like alternate interior angles. Like those would be alternate interior angles. They say alternate interior angles have to be equal. Alternate exterior angles, which would be those, must be equal. Corresponding interior angles, which would be those two, have to be supplementary. Corresponding exterior angles, which would be these. Yeah, I'm not going to make you memorize all that vocabulary because it's pointless. So we're going to define Hoff's rules. This is my claim to fame, darn it. This is me trying to get into the history books. Hoff's rule is, whenever you have a pair of parallel lines cut by a transversal, all angles are either equal or supplementary. And you can figure out which ones are which. not that hard. If they look equal, they're equal. If they don't look equal, they're supplementary. Well, that's the end of me making it easier for you. The next step, for you guys, what we've been talking about, just measuring angles and degrees is not adequate. In many cases, you guys are going to need to be slightly more precise than that. So let's say that this is a blow up of a single degree, which of course it's not, but it can be divided up into 1 degree is equal to 60 minutes. You know what the symbol for minutes is? Single quote, just like the symbol for feet. It is kind of tricky. 1 minute is then broken up into 60 seconds. Symbol for seconds, by the way, is the double quote, like inches. So you've got to be very careful. You got to know that you're dealing with angles, and that is not feet and inches, it is minutes and seconds. Use gradients. If that's what you're designing, then you can. But so, let's say we have an angle that is given as 47.3842 degrees. And we want to convert this. This is what's called DD notation for decimal degrees. We want to convert it into what's called DMS notation for degrees, minutes, and seconds. You got it. How do we do that? Well, just like if we had when we had our fractional feet, remember we made a big deal out of doing that, where you might have 14.73 or 783 feet, and I wanted it into feet, inches, and sixteenths. Do you remember how we did it? Well, the 14 just came off. We didn't use the 14. Then it was the 0.783. We did times 12, right? We're going to do the same process here. 47 degrees is just 47 degrees. We're going to take the 0.3842 degrees, however, and we're going to convert it. We know that 1 degree is 60 minutes. So now we take our 0.3842 times 60. 23.052. 23.052 minutes, that is. So now we're going to do the same thing. We're going to take off the 23. That's 23 minutes. We'll take the 0.052, and we're going to convert it into seconds. 1 minute is 60 seconds. Now on my calculator, I'm going to cheat. I'm just going to subtract 23. That way I don't have to punch the 0.052 back in. And times 60 is going to give me 3.12. It is okay to have 1 decimal place in your seconds. We usually don't go over 1 decimal place in our seconds. So this would be listed as 47 degrees, 23 minutes, 3.1 seconds. You'd be measuring with lasers to get to that precision. What's that? Well, for NASA, possibly. In my career, I have never seen anything. What's that? No, just to measure, you'd be using it. You'd have to use optics. You cannot physically measure. I've never even seen down to a second physically measured. The smallest measurement I've ever seen taken physically was down to the nearest 5 minutes. Yeah. Comparator? Yeah, most places will go down to like the nearest 15 minutes, like a quarter of a degree basically. Sometimes maybe 10 minutes at the most. So usually I've seen a lot of places will go down to 15 minutes. Bless you. Because it's tough to measure anything past that. one of the places where I've seen the CMM used, I've actually Hutchinson Technologies in Chippewa Falls. I don't know if they still do, but they used to have a CMM set up to measure to the nearest millionth of an inch. But to do that, the room had to be totally humidity controlled and temperature controlled, to the point where they actually had to program the room that a person was coming in, and so that the room had time to adjust, and the person had to get in there and wait. You actually went in there and just sat down basically, and the person in the control room waited for the room to adjust to you, so it got the humidity and temperature evened out for your body temperature and your exhalation. And that's not, yeah, it was interesting. And then once you start working, or of course, once you start moving, your body starts to produce a little bit of heat. So that person in the control room is monitoring constantly, and if you start to produce heat or start to sweat and it changes the humidity or temperature in the room at all, they'll say, oh, you got to stop for a minute. We got to wait for the room to adjust to you. Okay, well, for now, we're going to talk about this more tomorrow because we need to talk about operations with this stuff. I'm going to give you a packet here in a second, and then that packet's going to be page 266, 1 through 75 of the odds. Now, I realize we haven't talked about all of this yet. We haven't talked about operations with degrees, minutes, and seconds or any of that yet. We'll talk about it more tomorrow.